So now let's talk about what that constant means. So this is energy, or the Jacobi integral. On the Hamiltonian side, right, because H and L and all of those things have units of energy, sometimes people will say the Hamiltonian energy is constant. And it's important that they say Hamiltonian energy and not just the usual kinetic plus potential, because this is not kinetic plus potential. It's somewhat different. If you write out what this is, you could either write it as just the energy, and that's what I'll do. I'll write it as E. That thing that I wrote is little h or big H. Remember, little h was using the Lagrangian, big H was using the Hamiltonian. I'll use capital E. Capital E as a function of x, y, z, x dot, y dot, z dot. I'll call it energy, even if it's not. This is equal to 1/2 x dot squared plus y dot squared plus z dot squared plus the effective potential, which is a function of x, y, and z. This is a constant of motion. That means whatever you got for the initial condition, let's say your initial condition was x naught, y naught, z naught, x naught dot, y naught dot, z naught dot, that determines what the value of E is. And then as things change in time, all the terms on the right-hand side here have to vary in just such a way that this value on the right equals the original value. So if you haven't seen constants of motion, that's what it means. Geometrically, and that's how I'm going to interpret a whole bunch of things. What does a constant of motion mean geometrically? So this is without using any power or propulsion. Geometrically, this means the motion of the particle is limited to a 5-dimensional subspace of the full 6-dimensional phase space. And maybe you're thinking, big deal, but it is kind of a big deal. We're not used to thinking in terms of 6 dimensions. We think in terms of 3 dimensions. If our phase space, I don't know if you've seen the phase space perspective, but if you had 3 dimensions in which a particle could move, and I don't mean 3 spatial dimensions, I just mean 3 dimensions that describe the evolution of a system mathematically. From this initial condition here, this thing could move around, and who knows what it does. If it's constrained to be on a 2-dimensional surface, maybe it's a 2-dimensional surface that's not obvious yet, that means it can't go just anywhere. It means it's limited to just a 2-dimensional surface. A picture to have in mind might be the layers of an onion. And I think I really do have a picture of an onion. Wow. Check it out. Okay. Onions have different layers. You could have phase space having different layers. So the space is divided up into layers based on your initial condition that says what energy layer you're on. So let's say I was on this sort of second layer from the top. Then as the system evolves, it has to sort of stay on that layer. Can't leave that layer. So I'm showing it dashed when it's underneath the top one. You can't reach the other layers. There are different values of the energy. I also like to think of it in terms of Russian dolls. I think I got this in Poland. So this is a Russian doll, right? And it's got some interesting surface to it. And then inside, there's some other thing. And inside of that, there's something else. So you can view the 6-dimensional space of the 3-body problem as involving a whole bunch of nested layers that each have their own energy value. And if a particle starts on it, maybe you did a burn and you took it to that value, then it stays on that. And the only way to get off of that energy, I sometimes call it an energy surface. So I would say all of these layers here are different energy surfaces. And there's a continuum of energy surfaces. It's not like there's a gap, like as shown here, or with onions. It's a continuum, but you are still limited to the one surface that you started on. And this does have some important ramifications that are easy to interpret. Before I go to that, though, I do need to mention some terminology, because in the astrodynamics community and also the astronomical community, they don't often refer to this energy integral. They call it something else, right? They call it the Jacobi integral. It's related just by a factor of -2. That's worth saying. In the astronomical and astrodynamics communities, it's common to use. And I'll just use the symbol C. Some authors use something else. And so they use the Jacobi constant scaled. They write it as C, usually, and it's just equal to -2 times E. So you have to know which group you're talking to. And so then this becomes, the thing I don't like about this is the velocity shows up with a negative sign in front. So this has a negative x dot squared plus y dot squared plus z dot squared minus 2 u bar. So in terms of an energy perspective, everything's lost. Why are we doing this? But this is what's done. And if you wanted to, you could combine this into just v squared, where v is the magnitude of the velocity, the particle velocity in the rotating frame. So I think I would rather have just regular old E, where E is, at least looks something like energy. And physically, I've been saying, oh, the Jacobi constant is not the mechanical energy. Neither is E. So this is writing things in terms of the velocity in the rotating frame. If we tried to write E in terms of the inertial frame, what do we get? Let me use the things I used before. So C dot squared plus eta dot squared plus zeta dot squared. So that's 1/2 the actual inertial velocity squared. That means something in terms of the usual energy. And then this is minus mu1 R1 plus mu2 for R2. So that looks like the energy. But then we have minus h as a vector. This is the angular momentum of the particle. Angular momentum of the particle dotted with the n3 direction. Remember, that was the out of plane direction. The orbital plane of the two primaries is in the n1, n2 direction, so it's normal to n3. What we have, this is the kinetic, the true kinetic plus potential energy. I would say total mechanical energy. And then we have minus the z component of angular momentum. And if you were to ask me, well, why is that the thing that's constant? I don't know. So that's kind of weird. So we usually stick with things in just the rotating frame. So this is rotating versus inertial frame interpretation. I mean, there's some problems with doing things with the inertial, with R1 and R2. You have to keep track of where the masses are, M1 and M2, as a function of time. That's just a headache. So we typically don't do that. All right. So you have to know which community you're working with. And I might use E or I might use C, depending on the notes I have. But you need to be able to work with both. So let's talk about this potential energy and how it limits things. I want to insert that figure again, the Jacobi constant and realms of possible motion. If I write E, E is 1/2 the velocity squared viewed in the rotating frame plus u bar. Probably good to show that figure again of u bar. As the particle is moving around, its energy has to stay constant. Its velocity in the rotating frame, the magnitude is never going to go below 0. So physically, even in a rotating frame, you're always going to have the 1/2 v squared is greater than or equal to 0. And if that's the case, then the realm of possible motion, or the locations of possible motion, are those where u bar, x, y, and z, is less than or equal to the value of the energy. We usually don't use this phrase, realms of possible motion. The realm of possible motion, it's called the Hills region, after a celestial mechanician named Hill, who worked on this. And often what people will look at is where x, y, z equals E. This is the boundary of the Hills region, and it corresponds to where the velocity in the rotating frame goes to 0. So these are called the Hills surfaces. So this is where the velocity in the rotating frame, v, goes to 0. So they're called Hills surfaces. If we're looking in the full 3-dimensional circular restricted three-body problem, or Bill's curves if we're talking about just 2D, or they're also called the zero velocity curves. And the interpretation is pretty nice in terms of the figure that I've got here in the upper right. So if you have a certain value of energy, then it's as if you've taken a slice through here, and maybe it does some interesting things. Think of this as a mountain range, and we're looking at a topographic map, and we're looking at a constant elevation. There'll be some kind of weird shape that shows up. Maybe other parts of this will get involved as well. But depending on what your value is you increase in this energy, it'll go higher. That also means going lower in Jacobi constant. Let me show some cases of this. Because there are critical points on this surface, it's interesting to look at cases. First, let's just look at the 2D problem. So that means, z is 0 and z dot is 0. And that's okay. It's called an invariant surface, because if you do start in the xy plane, you have no z component and no z dot component, and you start in the xy plane, you will stay in the xy plane mathematically. So if we look at the 2D problem, we can look at the regions of possible motion. And sometimes people give them names and cases. Let me give you a version of it. So this is showing 5 different cases, and maybe you're able to see, starting with this upper left, this thing that we call case 1. Case 1 is where the energy is below a certain value that we call E1. What this means is that you've got an energy surface that's below the location of this L1 point, or the energy of that L1 point. If you have an energy that's below the L1 point, then what we're showing here is the region in gray is the region that is just not energetically accessible to you. So not accessible. Sometimes we call it the forbidden region. Makes it sound like we put some rules on it, but no, it's just 1/2 v squared would have to be negative in there, and that's just not physical. So that's not accessible. Instead, you could have motion around M1, so the larger primary, motion around M2, the smaller primary, or motion outside both of them. And the boundary is this black curve. Those black curves are exactly the locations where we have this condition. So U bar equal to E. And in that case, it would be U bar of just X and Y, right, equal to E, because Z is 0. Most of the orbits that we deal with in the two-body system are in this case 1. So it's not like case 1 is completely irrelevant. Think of this as the Earth-Moon system. If M1 was the Earth, almost every orbit is actually at an energy where it's very close to the Earth. It's definitely going to be in this region where nothing's going to make it go to the moon on its own. Also, if you had an orbit around the moon, it's going to be in this case 1. Now, things get interesting if you have a slightly higher energy than the L1 point. It probably is useful to think of this in terms of a spacecraft in the Earth-Moon system. So if we have now a larger energy, so GEO is not there. GEO is still in case 1. All near-Earth satellites are going to be in case 1. You need to do some energy expenditure to get to case 2. And I mean like real energy, low thrust or impulsive thrust. Pretty large delta V to get you to here. But in that case, a little bottleneck opens up right around the L1 point. And now it's possible for the spacecraft to go from an orbit that's around the Earth and then go to an orbit around the moon, or vice versa, or go to an orbit around an L1 point, if I were to zoom in, right? So that's for an energy that's greater than the energy of this L1 point, but it's still less than the energy of the L2 point. The L2 point would be right there, and it just hasn't opened up. So if you have slightly larger energy, now we're in this situation called case 3. And case 3, the spacecraft at P here, right, it can go from being in orbit around the moon, orbit around the Earth, or, it's in orbit outside of both of them. And sometimes we've given these names, like we've called the region that's inside the interior region, and the region outside we've called the exterior region. And then this region next to the secondary, you could either call that the secondary region or maybe the capture region. or maybe specific to the physical situation. So maybe we call this the moon region. This might look familiar from what I showed for that comet. The comet was actually in this case 3 situation with respect to the Sun-Jupiter system. That shape that you saw, it vaguely resembled this C shape. And so it came in from the outside. It kind of went past L2 and L1 and then went around. I guess it just went around once, kind of in the rotating frame, and then went back out. What's the next thing that happens? If you increase the energy again, let me go back to this picture of the potential energy. So the lowest energy point is L1. The next highest is L2. The next is L3. So if you go to a larger energy, now there's a neck that seems to open up at L3. And so that thing that looked like a C shape now looks like 2 tadpoles. So the particle can basically go anywhere. It doesn't have to go through L1 or L2. I mean, the orbit's not going to look like that. You get the idea. The boundary is called the zero velocity curve because what actually happens is that if a trajectory comes close to that, the velocity in the rotating frame is slowing down, and you actually stop and seem to bounce off in a cusp shape. If it doesn't exactly touch it, it'll seem to get close and then do some kind of loop-de-loop. But the velocity does actually go to 0. If a trajectory touches that surface, it goes to 0 velocity, and then it goes back out. Not exactly some kind of mirror image. There may be some kind of mirror image symmetry with respect to the line at which that's normal to where it hit, but there may be some interesting study related to that. So this is for an energy E that's greater than the energy of L3, but it's less than the energy of L4 and L5. So if you look over here, L4 and L5, you might be able to tell they've got equal energy. They've got the highest energy, at least on the surface. So if you have an energy that's above those, there is no inaccessible region. So everywhere is technically, at least according to this energy argument, it's accessible. Everywhere is accessible, at least by energy. There may be some other constraints that we don't know about and might be more subtle. So this is for an energy that's greater than L4 and L5. And here's L4 and here's L5. I think that's the convention. You do have to watch out. Some authors will order these in different ways, but I think this is the most unambiguous way because it's ordering by energy, L1, L2, L3. It's also what NASA uses. They call the one that's between the two massive bodies L1, the one that's on the other side, the secondary L2, and then the other one L3, and then L4 and L5 have been called L4 and L5 forever. And I don't know why they're left as last, but energetically, it makes sense. That's what zero velocity curves are. And remember, this was just for the planar case. If we're looking at the 3D case, the energy boundary isn't just some curves. It becomes actual surfaces in 3-dimensional space. So let me show you some schematics in 3D. In 3D, what do we get? So this is showing, it's hard to see the whole thing, so we're taking cuts through. So this is the energy of L1, and we're taking on the left, this is a slice at Z equals 0, and you can sort of see that C shape, right? So that would be what you would get in the planar problem, is that C shape. But now we also now take a slice at Y equals 0 here on the right, and you can get another idea of what's going on. So how do we interpret this? This would mean if you were in an orbit around M1, you'd be stuck in this sort of capsule region. You couldn't leave at that energy. And if you were to hit the boundary, you'll go to 0 velocity and then bounce back off. It's sort of like a weird game of billiards played in a rotating frame. So that's the energy at E1. Here's the energy at E2. So that's the energy of the Lagrange point, L2. And you could see now a bottleneck has opened up around L1. So this would mean that halo orbits are possible at L1, but not at L2. If you were to get to the L2 point, you'd actually just sort of stop and then bounce away. And then you could probably guess, okay, what happens at L3? If at the energy of L3, now we've got things sort of pinched down to a point at L3, and there's bottlenecks opening up at L1 and L2. It's interesting to look at these surfaces. If I use them at all, I'll mostly just look at them projected onto the z equals 0. So that would be like this sort of C shape. This is where the tadpoles start forming. So you get those 3D surfaces. Well, they're not 3D. They're actually, technically, they are two-dimensional surfaces in 3D space. 2D surfaces of zero velocity in 3D space. And they limit the motion. If you're going to design a mission that actually leaves Earth's gravity, then you don't have an energy of case 1. You need at least an energy in this case 3 situation. Usually, trajectories that leave the Earth on an interplanetary mission to Mars are in case 5. So they're not necessarily being the energetically most efficient because they're trying to get there quickly, right? Do a Hohmann transfer. Same thing for trying to get to the moon. If you wanted to get to the moon, you couldn't do it in case 1. You at least have to be in case 2 to just energetically get to the moon. Any comments or anything?
Dr. Ross, is there, so we've got this 5 constraints and 60 space. Is there a useful corollary, like with these drawings, but in velocity? Or is that like a visualization people draw or care about, or am I off there?
That's a great point. Yeah, I've tried to do something with this. So let's say we're talking about case 3, and I'm going to try to freehand what things look like. Here's M1, here's M2, and then I'm drawing the zero velocity curve. If I have a spacecraft that's far away from the zero velocity curve, I could write a circle of velocities. This is a circle of all the possible velocities I could have, and it has a radius of v, where 1/2 v squared plus u bar equals e. So I could write this also as 1/2 v squared equals e minus u bar, or 2e minus u bar square root. This circle shows all the possible velocities I could have. So maybe I've got something pointing in this direction, or maybe it's in that direction. Maybe it's in this direction. And so a little bit later, I'll be at some different location. And since I'm closer to the zero velocity curve, the size has to get smaller. If I get closer and closer, it's getting smaller until this circle of my velocity actually shrinks down to a point. And I've got no velocity when I hit the zero velocity curve. And then as I bounce away, the circle of possible velocities grows and grows. So that's another way to try to interpret things. It hasn't been used much. We did it in one paper. It might end up being pretty useful. Does that sort of answer your question?
Yeah, it does. And a follow-up, are there such a things as the regions of forbidden regions and stuff for velocity, or is that not the right way to think about it?
I'd say it's not the right way to think about it. These places that we call inaccessible, they are the places that are inaccessible to velocity, because your velocity square would have to be negative. It's just not possible. So we're actually using a constraint on the velocity to find a constraint of where you could be in position space, at least in terms of the rotating frame.
Okay, understood. Thank you.
Right? Like to be here, your velocity would have to be negative. You just can't do that. There are separate constraints that you can get, but you can't just look at the energy. There's things like quasi-periodic motion, and geometrically, that means the motion is happening on some kind of torus, but in the phase space, not in just this position space. That's a more advanced topic that maybe we'll get to, but that also does put constraints on what the velocity can be. It's just more subtle.
Okay, thank you.
Yeah. Anything else?
Dr. Ross, I have a question. So obviously, when you say bounce away, quote, it's not like a transfer of energy. It's kind of like if you throw a ball straight up on Earth, it'll eventually hit its point, its peak, and then come back down. It's like it'll hit zero velocity and then change direction.
It's zero velocity in the rotating frame. So I think maybe looking back at that video of the comet's helpful, because you could see the comet's about to hit the zero velocity curve, right? But that's only in the let me back up, right? It hits that zero velocity curve almost. That just means it's going at a speed that in the rotating frame corresponds to 0, but you don't see anything in the inertial frame at that point. And then it slows down, almost seems to be hitting the zero velocity curve at a few spots. And there's, let's say this last one here, there's really nothing special about that from the point of view of what's happening in the inertial frame. But you could see that as it gets further away from that zero velocity curve, it's moving faster because the velocity is faster. So it's all connected.
Okay, yeah, that makes sense.
Yeah. I didn't say what these green trajectories are, but I may as well tell you. So they're related to orbits around L1 and L2. So these are the green trajectories are things that start at, you can think of it as a halo orbit, like what James Webb is on, but for the Sun-Jupiter system, they leave and return to the same halo orbit. So it's sort of this bizarre phenomenon. And we just sort of overlaid it because we said, oh, maybe this provides sort of a skeleton for how the comets move. I've sort of moved away from that point of view, but I haven't remade the video. So I just keep those green trajectories in. And it almost looks kind of like it's following them, but not exactly. All right. So critical points here, just sort of revealed by the energy where these equilibrium points are. And we're just going to have to continue with that next time because I've run out of time for today.
If you appreciated this video, please like and subscribe, or just wait and watch the next video in the series.